So, so this is actually steady state error. That means in that case what we will get, that area 2 also has area 2 generators also they have to it has to respond, right. So, in that case you will get, I mean if you put, and just from that expression if you put it, you will get simply minus delta PL1 upon beta 2. Now, if you look into that, your just hold on, right. So, this is coming minus delta PL1 upon B2, right. This one your, if we look into this, that this one minus delta PL1 1 minus your 1 by say beta 2, right. This is after simplification. So, I showed you how to make it, right. Then another one for area 2, whatever we have seen, right, that is your minus, if we add both, minus delta PL1 and beta 2. If you add both, you will find that it is coming minus delta PL1. The meaning is that if even if the load disturbance has occurred in area 1, area 1 generator is not accommodating all the load, right. For different, for B greater than beta, we have taken 2 beta, right. So, in that case what will happen, that your part of the generation will be, has to be shared by the generator of area 2, that is the meaning. That is why best choice is that your B is equal to beta, that is that frequency bias should be equal to area frequency response characteristic, right. So, that is the meaning. So, this one that I showed you how to make it. So, this one you will find out that minus delta PL1 1 minus 1 upon beta 2, right. Some mathematical you are what you call simply things you have to do it. So, now next so this is actually what like this, right. Next is that your, this is already I told, so not telling again. Next is that controller, integral controller, right. So, in that case just hold on little bit make it. So, this one in the second case your, this is minus Ki integral controller. So, this is B1 delta F1 and this is the structure of the integral controller, and delta p ti 1 2 is coming, these two are added, and this is that area control error 1 and this is output U1, right. That I told you initially, U1 is equal to integral of minus Ki 1 integral of AC1 dt. Similarly, for this one also, that U2 is equal to your AC2 minus Ki2 integral of AC2 dt. So, this is delta p ti 1 2, that means this is actually delta p ti 2 1 is equal to, we have seen in the previous lectures, into delta p ti 1 2, right. And this is the frequency bias for area 2, this is delta F2 and this is the U2. This is actually control your what you call the control structure, controller structure for only for integral controller I have shown here, right. So, now figure 2.2. So, actually parameters, whatever parameters till now we have used R1 is equal to R2, R is equal to 2.40 hertz per unit megawatt, Kp1 Kp2 we have taken 120 hertz per unit megawatt, Tp1 Tp2 power system time constant Tp we have taken 20 second, governor time constant for all the cases we have taken 0.08 second, and steam chase time constant we have taken 0.32, and T12 that your synchronizing coefficient we have taken 0.0866. Actually, how this thing taken, that T12 is equal to V1 V2 upon X12 cosine of delta 1 0 minus delta 2 0. We have taken X12 is equal to 10 per unit, right, and V1 is equal to V2 is equal to 1.0, and delta 1 0 minus delta 2 0 we have taken 30 degree, right. So, if you do so, so it will be actually cos, it is 1, so cos 30 upon 10, because X12 we have taken 10 per unit, right. So, cos 30 is 0.86 divided by 10, 0.0866, that is why this T12 is 0.0866, right. And we have taken equal area capacity. So, A12 is minus 1, there is no load disturbance in area 2. So, delta PL2 is equal to your 0, and integral gain setting we have taken Ki1 is equal to Ki2 is equal to 0.67, and load disturbance in area 1 we have taken delta PL1 is equal to 0.01 per unit megawatt, right. So, in this case, for this case, your what will happen, the dynamic responses, right. So, let me clear it. So, these are the parameters we have taken, and dynamic responses in the classroom exercise we cannot do simulation, right. So, this is a frequency deviation, right. Let me your what you call reduce that volume to 100%, right. So, this is actually frequency deviation. Delta, when it is uncontrolled dash line, it is showing steady state error, right. No integral controller, dash line is no integral controller, Ki1 Ki2 is equal to 0, and when you put integral controller, steady state error, that frequency deviation steady state error for area 1 area 2 both are reaching to 0, right. So, and this is your tie line power, at steady state tie line power deviation is 0.005, right, minus 0.005, and at state, and when integral controller is there, it is actually 0, right. So, if 1% load disturbance is you are giving, and your what you call that, you will find that tie line power is coming minus 0.005. So, just half of delta PL, right. And similarly, your delta Pg1 and Pg2 load disturbance has happened in area 1, when uncontrolled both are generating your 0.005 megawatt, because both are uncontrolled. So, both areas sharing the same generation at steady state 0.005 0.005, right. But when area control is there, for frequency bias I told you B is equal to beta. So, B1 is equal to beta 1, B2 is equal to beta 2. So, area 1 generator will accommodate all the loads. So, it is your what you call 0.01, this one is 0 Pg1, this, and delta Pg2 it is coming back to 0, because that that load disturbance in area 2 is completely unobservable by the supplementary controller in area 2 following a load disturbance in area 1, right, when B1 is equal to beta 1 and B2 is equal to beta 2, right. So, this is actually your what you call this responses, right. So, this is what has been shown. So, that is why this figure 2 what I showed, that it is seen that with the integral control action delta F1, delta F2 and delta P tie 1 2 are settling to 0 for a step load disturbance in area 1. Note that without integral control, load increase in area 1 is equally shared by both the units, that is delta Pg1 is equal to delta Pg2 is equal to 0.5 PL1, half of PL1. So, 0.005 per unit megawatt. With integral control action, delta Pg1 is equal to delta Pg1 PL1 is equal to 0.01 per unit megawatt, and delta Pg2 is equal to 0, right. So, that is why we have to use that some controller. So, right, later we will see little bit more, but in the classroom we cannot do simulation studies, but some ideas you have from the steady state point of view. So, now we take another example, another typical example. So, here your figure 23 shows two area interconnected system. The load in each area varies 1% for every 1% change in system frequency, right, and F0 is equal to 50 hertz, R is equal to 6% for all the units. Area 1 is operating with a spinning reserve of 1000 megawatt spread uniformly over a generation of 4000 megawatt capacity, and area 2 is operating with a spinning reserve of 1000 megawatt spread uniformly over a generation of 10,000 megawatt. D1 is equal to given that 380 megawatt per hertz and D2 is equal to 800 megawatt per hertz, right. So, we have to these are given, these are the area 1, area 2, everything is given, right. So, load here is 20,000 megawatt and load that is given your 40,000 megawatt, and generation this side is given. So, determine the steady state frequency, generation and load each area and tie line power for the following cases. Loss of 1000 megawatt load in area 1 assuming that no supplementary controls, right. So, this is one, and another one Another one, each of the following contingencies when the generation carrying spinning reserve is in each area is on supplementary control with B1 is equal to 2500 megawatt per hertz and B2 is equal to 5000 megawatt per hertz. So, number 1, that loss of 1000 megawatt load in area 1, right, and loss of 500 megawatt generation carrying your what you call carrying part of the spinning reserve in area 1, right. So, solution. So, in this case what will happen, the 6% regulation of 20,000 megawatt generating capacity including spinning reserve of 1000 megawatt, right, in area 1. So, 1 upon R1 is 20,000 by 6% of 50 hertz, right. So, it is 6666.67 megawatt per hertz, right. So, similarly your 1 upon R2 will be, it is actually I think it is load here, it is given something, just hold on, I think it is 42, right, 42,000 megawatt. So, this one we have taken that your 1 upon R2 is equal to your 42,000 upon 6% of 50. So, 14,000 megawatt per hertz, right. So, now 1 upon R is equal to 1 upon R1 plus 1 upon R2. So, that is 2, if you add both it will be 2667.67 megawatt per hertz, right. Therefore, D is equal to, if you add D1 plus D2, so it will be 380 plus 80, 800, so 1180 megawatt per hertz. So, delta F SS is minus delta PL upon D plus 1 upon R. So, that 1000 load loss, so it is minus of minus 1000 because increase will take positive sign and decrease will take negative sign. So, if you make it that total D is this much and 1 upon R is this much. So, delta F SS is 0.04577 hertz, right. Now, load changes in the two areas due to increase in frequency. We know that D into FSS, right, because D we have taken the constant that load is sensitive to the change in your frequency. So, delta PD1 will be D1 into delta FSS. So, D1 is 380 and delta F steady state is just we have got 0.04577. So, this is 17.392 megawatt, right. Similarly, delta PD2 will be D2 into delta FSS is equal to 800 into 0.04577 megawatt, that is 36.616 megawatt, right. Therefore, we know delta Pg1 steady state minus delta FSS upon R1, that we have seen before. So, it is minus 0.04577 into your what you call that 1 upon R1 is this much. So, minus 305.13 megawatt. Similarly, delta Pg2 minus delta FSS upon R2. So, again minus 0.04577 into 14,000. So, minus 640.78 megawatt, right. So, part B. So, no, this is your now new load in area 1 and area 2. So, load in area 1 now 2000 and 100 loss. So, 2000 minus 1000 plus this D into delta FS term. So, 17.392. So, 19,017.392 megawatt. Similarly, load 2 will be your this one actually will be 42 actually, right. So, it will be 42. So, 42,000 plus 36.616. So, whatever it comes 42,036.616 megawatt. Now, generation in area 1, right, just generation in area 1 and area 2, it will be 100 or 19,000 minus this much, right. So, it will be 18,694.87 megawatt and Pg2 will be 41,000 minus 640.78. So, 40,359.22 megawatt and P tie 2, the actually your what you call that your it is flowing 2 to 1. So, P tie 2 1 will be, because they are in the diagram direction is given 2 to 1. So, it will load 1 minus Pg 1. So, this is the load 1 minus this is the Pg 1. So, it is 322.522 megawatt, right. Now, with supplement B, with supplementary loss of 1000 megawatt load, right, in area 1. Area 1 has a generating capacity of 4000 megawatt on supplementary control, and this will reduce generation so as to bring AC1 to 0. Similarly, area 2 generation on supplementary control will keep AC2 at 0. So, we know that AC1 is equal to B1 delta F1 plus delta P tie 1 2, it has to be 0. AC2 also B2 delta F and A12 is minus 1, say we have taken a same area your capacity. So, minus delta P tie 1 2 is equal to 0. Hence, delta F is equal to 0 and delta P tie 1 2 is 0, right. So, area 1 generational load are reduced by 1000 megawatt. So, there is no steady state change in area 2 generational load or the tie flow, right. Now, loss of 500 megawatt generation carrying part spinning reserve in area 1. So, spinning reserve lost with generation losses, it will be simply 1000 by 4000 minus 1000 into 500. So, 166.67 megawatt, right, simple arithmetic. So, spinning reserve remaining is 1000 minus 166.67, so 833.33 megawatt. This is sufficient to make up 500 megawatt. Hence, the generation and load in the two areas are restored to their pre-disturbance values. So, there are no change your what you call, there are no changes in system frequency or tie line power flow. This is a typical problem, right. So, this is what I have made it from my side. I suggest that you please do from your side and derive all these things. By chance if you get any error or anything from my side, you just put the question in the forum or you please send a mail to me, right. Next is the generation rate constant. Actually, every your what you call, every generating unit, it has some limit to generate power. Suppose that load demand suddenly had increased to 20 megawatt. So, generator cannot generate that 20 megawatt power immediately, right. It has some your limitation, right. I mean just it cannot, it takes some time, right. So, that and similarly that every generating unit, it has some rate limit, accordingly the power will be your what you call chase the load, when power generation will chase the load. So, in establishing AGC signal, right, it should be, just hold on. So, generation rate constant. So, in establishing AGC signal, right, it should be recognized that there is a limit to the rate at which generating unit outputs can be changed. This is actually particularly true for thermal units, where mechanical and thermal stresses are the limiting factors. Hydro case, that these limits are so high that generally it does not your what you call. So, generation is very fast for hydro. If time permits, at the end we will see, right. So, but for thermal it is stringent type, right. So, shows the flow chart for incorporating the effect of generation rate constant. I will show you, right. So, in the matrix differential equation, x dot is equal to x plus bu plus gamma p, right. So, for obtaining the system response at various states, at each time interval delta t second, so right, for integration the generation rate is checked for its magnitude and sign. That is, for the kth interval, the generation rate delta pji dot, say at kth interval, this is I generating unit, are less than or equal to a specified maximum rate, say r, the corresponding generation changes, right, the delta pgi k is not altered. In case it violates, right, the generation rate exceeds the maximum specified rate, the generation change is constant to the relationship of this one. The delta pgi, that is at kth interval, is equal to delta pgi k minus 1 plus minus r into delta t. That how we get this one. Suppose only I am making it. Suppose this is your turbine generator, right, block diagram is there, whatever, then this is my delta Pg. So, you have the rate limit, right, this side is R and this side is minus R, so same, increase or decrease it is same. Generally for thermal unit it is same, for hydro unit it is not, it is different, but it does not violate the constant. So, every time, every sampling instant, right, or every integration instant you have to evaluate it. How we will do that? That first you find out what is delta Pg dot, right, delta Pg dot, right, you can make it that you just hold on, here I am making it. Suppose delta Pg your what you call, say a delta Pg k, say dot is equal to delta Pg k plus 1 say minus delta Pg k divided by the delta T, right. This first you have to make, then you check the absolute of this one whether it is greater than R or not. So, generally you check the whatever is made it here, that absolute delta Pgi kth interval dot whether it is greater than equal to R or not, right. So, first you check, so that means we are not checking plus or minus, increase or decrease, first you check whether it is greater than R or not. If it is a greater than less than R, then no need to consider this, right. So, it is not violating the constant. If it is this absolute is greater than R, then you check whether it is your what you call whether it is positive or not. That means you check that delta Pgi k dot whether it is greater than 0 or not. After that check positive or not. If it is positive, right, if it is positive, that means you constant it to R. That means your delta Pgi k your what you call k minus delta Pgi your k minus 1 divided by delta T is equal to your R. That means delta Pgi k is equal to, you can write delta Pgi k minus 1, I have made it in bracket, this is k minus 1 plus R into delta T, and if it is why I have made minus, if it is less than 0. Suppose if your delta Pgi k dot if it is negative less than 0, in that case it is delta Pgi, right, k minus delta Pgi k minus 1 divided by delta T is equal to minus R, right. So, both increase and decrease rate we have taken same R. So, in that case it will become delta Pgi k will become that delta Pgi k minus 1 minus R into delta T. That is why we have written that delta Pgi k is equal to delta Pgi k minus 1 plus minus R into delta T. As long as limit will be violated, the generation response will move like a ramp, straight line increase or decrease, it will move like a ramp response, right, because it is a straight line. As long as it is not violated, at that time oscillation will start, small oscillation will start. So, that means now this is the flow chart. First is store delta Pgi k minus 1. Every sampling instant on this thing you have to store this value when you write the code. Next, solve x dot is equal to x plus b plus gamma p and evaluate the your states at the end of kth interval. Actually, what you are doing nowadays, that you have a MATLAB simulating thing, you are just putting all these things. But if you write your code, this generation rate you have to consider separately, right. So, MATLAB also, those who have written the code, they have also considered everything, that limiting all type of limiter, limiting value what will be given. Simply you are giving every output block limit your rate limit and you are getting the response, and generation rate constant actually it deteriorates the dynamic responses. But you have to when you write the code of your own, then you have to write all these things, right. So, next is that we are checking that absolute of delta Pgi k greater than R or not, right. First you have to check, if it is no, then directly you will go, but if it is yes, then you check whether it is greater than 0 or not. If it is a positive, then this side left hand side it is delta Pgi k is equal to delta Pgi k minus 1 plus R into delta T. So, it moves like a straight line because R into delta T plus this one, and if it is negative, then your delta Pgi k will be delta Pgi k minus 1 minus R into delta T, right. After that you write all T delta Pgi k dot etc, right, all the state variables, and then your this is the flow chart. So, this is for generation rate constant. So, generation rate constant actually deteriorates the dynamic responses, and how actually, if you say here how actually generation responses goes. Suppose 1% step load disturbance is there, and when generation rate constant is there, your integral gain will be very small, right. When you are not considering any generation rate constant in your simulation studies, integral gain will be higher. For example, whatever simulation I have shown you, that Ki1 is equal to Ki2, we have taken 0.67. This is without generation rate constant, right. But in reality, this generation rate constants are there for any thermal unit. So, in that case, the integral gain should be very small. For example, Ki1 will be equal to Ki2 say is equal to 0.07 or even less, right. So, it is a very small, otherwise what will happen, your system will become unstable for higher gain. So, you need very small gain. This is one thing, and dynamic responses also will deteriorate, right. It will not settle in 10 or 15 seconds, it may continue for long, right. And in addition to that, that although time is not there to consider that a governor deadband is also there, right. So, if you consider that one, that governor deadband has effect of your what you call sustained oscillation, that oscillation will continue for long if you include the governor deadband. And in that case what will happen, suppose you have 1% step load disturbance and suppose you are plotting some generation, say this is my time and this side says some delta Pg. So, initially what will happen, because of the rest for non-reheat type, right, for non-reheat type your what you call generation rate constant, say R is equal to 10% per minute, right, that is 0.1 per unit megawatt per minute, right. If you consider that responses, suppose your disturbance is say this line is say 0.01 per unit megawatt. So, response initially it may be like this, ramp, it will go like this, and finally when response, when the constant will not violate, at that time it will show some oscillation, it will settle to 0.01. Otherwise, we will find that it is a straight line increase, decrease, ramp increase or ramp decrease, right. So, and settling time will be very high. For theoretical purpose, that is what you call that this some 60 or 80 seconds or even more, right. But in reality, if you go to the control loop and try to see that frequency cannot be like ideal case like the way you got for a step load disturbance, because power systems continuously loads are switched on and off. So, continuously if you see the control room, that continuously will find that frequency is changing, but anyway it is not losing synchronism unless and until some abnormalities happen in power system. And generation also, if you see like this, you will find it is not like settling or this thing, it is some throughout the day generation is changing, because load is also changing throughout the day, right. So, this is generation rate constant. Another thing is that discrete integral controller for AGC. Look, any system, if you see any system, you will find that any system actually is a continuous system in reality. A power system also itself is a continuous system, right. So, but so your power system is a continuous system, but controller part can be put in discrete domain, where the power system is in your continuous domain, right. So, so in reality that controller must be in discrete domain. So, in that case what will happen, that for easy operation and control, an interconnected power system is generally considered an amalgamation of a number of areas. So, interconnection between your what you call your contiguous areas are physically remote from the dispatch center, right. So, it is usual practice to sample system data, that is frequency and type power, hence the area control error. So, you have to sample the frequency and type power and combine them together, right. So, at every that means at every sampling instant you have to your what you call sample that area control error for each area, right, and your what you call and transfer this information over data links to the dispatch center. And when you are transferring this to the dispatch center, there is some delay associated with that, but we will not consider that. The delay is very small, but we will not consider that. These signals are updated at every 2 seconds, 4 seconds, even up to 8 seconds or 16 seconds or even 32 seconds also, right. So, not immediately, right. This actually reduces the wear and tear of the controller part, right. So, it will increase the life your what you call of the controllers. So, this figure 25 shows such kind of one thing. So, what happened in this case, a power system is there. A power system, we know that x dot in mathematics, x dot is equal to x plus bu plus gamma p. This is in continuous time domain. Then you have a sampler, right. This sampling time may be t is equal to 2 second, 4 second like this, right, or 8 second, 6 second like this, or 1 second like this. So, that means output here, suppose the output here is your ACE, you are sampling frequency and type power, combining this both B into delta F, B1 into plus delta P tilde. And after that this controller is here, then you make a 0 order hold, right. like till the next sampling instant comes, this 0 order hold actually hold this output of the controller, right. Suppose you take t is equal to 2 second, right, t is equal to 2 second. So, controller will if it is an integral controller only, you will be computed. After that, till the next sampling instant comes, then 0 order hold will hold that signal, right. And but this is you are solving continuously. This is you are solving continuously mathematically. Suppose you have taken integration step length is 0.005 second for solving this one. This is okay, but till next sampling instant come, the same signal will be going to that. I mean, suppose that t is equal to 4 second, you got something, and next suppose t is equal to 2 second is the sampling time. Suppose that t is equal to 4 second you have taken, next sampling instant come, t is equal to 6 second, till 6 second this u, that output of this one, because 0 order hold will hold it, right, and send the same signal to this till the next sampling instant come. That means that every time increment till next sampling instant come, that u will be continuous, that constant u in between two consecutive sampling instant will be fed to the power system, right. This is the philosophy. Okay, thank you very much. Much more we'll discuss for deregulated power system, another thing, but in the next lecture. Thank you very much.